All right, so today's going to be an extension of what we ended with last week with the fundamental theorem of calculus, specifically the second part. Now, something I don't think I said last week that just wanted to let you know, I don't really know why this is the case. Usually when things are published and titled that they stay consistent, the part one and the part two of the fundamental theorem of calculus, depending on what source you look at, they switch which one is part one and which one is part two. It's not like when Newton or Leibniz published this stuff, they're like, this is the first part, this is the second. Just over time, it's been broken up into two parts. I was reminded of this when I was going through my CUDA software that generates worksheets. And in CUDA, they actually reverse part one and part two. So their part one is our part two, and their part two is our part one. So don't try to commit to memory which is part one and which is part two. It's really not that important. What's important is that you know both parts of it. So I titled this just using the fundamental theorem of calculus to evaluate a piecewise function. And we are using the fundamental theorem of calculus. It's just that we are using the part of the fundamental theorem where we are taking the antiderivative and then evaluating it at the upper bound, at the lower bound, and then subtracting them. Now, since it's a piecewise function, that means that we have multiple functions that are going to add together to give us the overall area. So I generated this piecewise here. It's going from 0 to 2, and the function it's following is y equals 2x. And this one here is y equals 1/2 x cubed from 2 to 4. This one I'm going to do in purple. This one I'm going to do in green. So on the left here, I went ahead and sketched about what it could look like. So from here to here, it ends at 2, 4. So the purple area is what I'm going to find over on the right here. And then this is the 1/2 x cubed, which is going to find in the green. So I set up a definite integral from 0 to 2 of 2x dx. And I took the antiderivative of 2x, which would just be x squared. Again, double check your work by taking the derivative of it. If I bring the 2 down, reduce by 1, I get 2x, so I'm happy. And then I put this vertical line in to show them evaluating from 0 to 2. So if I plug in 2, plug in 0, I get that the total area of this little triangular shape is going to be 4, which also by what we're doing, the geometric shapes under the curve, if you would have recognized that this was a triangle, which obviously you do, it has a base of 2 and a height of 4. So half the base times the height would equal 4. So it works out nicely. Now this one here, we have a trapezoid. And so instead of looking at the geometric shape, again, I'm just taking the antiderivative of it. So I know that this 3 has to become a 4. And I think to myself, well, I'm going to be bringing the 4 down. So I know I'm going to have to multiply something by 4. So I went ahead and I divided this fraction by 4 to give me 1/8. Because if I know that the first thing I'm going to do is multiply by 4, I should have divided so that the 2 cancel out. And so I get 1/8 x to the 4th. And then I evaluate that at 4 and at 2, subtract them, and I get 30. So the area of this green trapezoid is 30, and the area of this purple triangle is 4. So therefore, the area of this entire shape will be 34. Your homework tonight is 4 problems, and they are giving you something that looks like this with each corresponding function. I'm asking you to do what I did on the right, write a definite integral, find the antiderivative, evaluate it, subtract it, add it, smile, you're done. All right. I'll be in Zoom if you need anything. Try those out. And yeah, good luck and happy Monday.